Okay, time is 11 o'clock. Let's begin here. So project number 3, we will talk about this project later today. Notice the tentative due date of Wednesday, October 24th. Are there any questions before we begin? Okay, we are starting a new chapter today, chapter 6. Chapter 6 discusses multiple regression. What that just basically means is now we're going to have more than one predictor variable in our model. And we will have this basically throughout the rest of the course. Now, just to help set this up, then let's just do a very brief three-dimensional algebra review. Meaning, let's say we have two independent variables and one dependent variable y. And so we have this simple equation y is equal to 1 plus 2 times x1 minus 3 times x2. If one wanted to plot this, of course, all you would need to do is plug in various values for x1 and x2, evaluate our equation to get the corresponding value of y. And that's what I've done here to get 4 particular points that we could plot in 3 dimensions. And these points are represented by the red dots there. And then once you plot those points, then you can join those points with a plane, since we're in 3 dimensions here. And so that's what the plane looks like with respect to the axes shown in that format. If we were to look from above, we could see the plane like this. And if we were to look at it at exactly at y equal -3, this is what the plane would look like in that configuration. And so when we have now 2 predictor variables to predict one response, we're always going to be able to generate a plane like this to represent the estimated, or I should say the sample regression model. And we will do that shortly. So to review what we've been doing with simple linear regression, simple corresponds to only having one predictor variable. Again, this is the diagram that we looked at the very beginning of our course, where we have this population, and we're interested in certain characteristics about the population represented by y and x. In particular, we would like to use x to predict y. We would like to know the relationship between x and y. The way that we represent that relationship is through our population regression model. Of course, I could represent the model like this as well. Expected value of y is equal to beta 0 plus beta 1 times x. In particular, this beta 1 really tells us some information about the relationship between x and y, or expected value of y. Now, in order to get beta 0 and beta 1, we would need to know all the particular values in the population. Usually that's going to be unrealistic. So what we do in the statistical science then is we take a representative sample from within the population, and with this representative sample, it's going to be a smaller set of information that's going to be more manageable to work with. And through equations that we've seen, we can calculate our sample regression model, y hat equal to b0 plus b1 times x. B0 estimates beta 0, B1 estimates beta 1. Now, because we can also get the sampling distributions or probability distributions for B0 and B1, that allows us to do this part right here, the inference part. Inference means that we do confidence intervals, we do hypothesis tests about population quantities. This is the big picture of what we do in the statistical science, represented in terms of regression analysis. We also looked at particular graphics such as this, where we have in the green dots represent actual population values. And each of these green dots, you can get to them by using our regression model, if you somehow knew beta 0, beta 1, and the corresponding epsilon. For a particular x, you can look at what we would expect y to be on average, and that's what's represented by the red line. Notice how the red line goes through the middle of those points. If we were to take then a sample, let's say those yellow dots represent our sample, then we can try to estimate that red line through using the calculations that we've discussed in the past. And the blue line then represents then our sample model. The purpose of the blue line is to estimate the red line. As you can see, it's not perfect, but it gets at the general idea that there's an upward trend. Okay, so nothing new there. Let's translate this now on to a multiple linear regression setting. Multiple meaning that we have more than one predictor variable. So this is how our diagram involving those circles now translates to this particular setting. Now we have predictor variable 1, predictor variable 2, down to predictor variable p minus 1. Now I might be wondering, why don't I just say we have p predictor variables? It would be a lot easier to say. Well, some books will do that. Other books will say you have p minus 1 predictor variables, like our book does. Because notice how many beta parameters do I have then? P. So it just shows to keep the p corresponding number of beta parameters. Again, the first subscript here, I, corresponds to, let's say, the particular, eventually, observation number or particular value of the item that we have. So it's just a general way to say that. And notice how, also I should say, this epsilon is still going to be distributed independent normal 0 sigma squared. And remember what this epsilon is basically representing. x1 through x of p minus 1 do not necessarily account for all the variability in y. They are not going to be perfect predictors of y. And what this epsilon is basically representing is all the other information that we can't measure, or maybe we didn't measure. It's all sucked up into this random error term. And we say that on average all the errors are 0 with a variability that we denote by sigma squared. Over here in the sample, we have corresponding statistics, B0 through B sub p minus 1, that again estimate the betas. And once again, we are going to be able to calculate these B quantities. We will be able to figure out what their sampling distributions are, and this will allow us to do inference, then back to the population, to do confidence intervals and hypothesis tests regarding betas or other similar quantities. So that's the extension, not that difficult. Well, what happens if we only had 2 predictor variables? Let's look at what this would look like graphically then, to make sure you're following this idea. So imagine that we have a 3D plot where we have x1, x2, and then coming up is y. Represented on this plot, in comparison to what we had just seen before, is now just one point in the population. Just one, because it's hard to represent multiple points. So this is what the point looks like. Let's say the point falls right here, that yellow point. And so that's an x1, x2, y, you can say triplets. Based upon our assumed regression model then, if I knew beta 0, beta 1, beta 2, and also epsilon, I could get the exact value of y. Well, what would we expect y to be on average? Well, that's where we drop off the epsilon, because its mean, of course, is 0. And so expected value of y is beta 0 plus beta 1 times x1 plus beta 2 times x2. And since there are 2 predictor variables, 1 response, we can graph this in 3 dimensions with a plane. And so that's what perhaps the plane would look like. Again, this plane would go through the middle of the, if there was more than one yellow point, it would go through the middle of all those yellow points. Again, it represents, given x1 and x2, this is what we would expect y to be on average. The distance from the plane to the yellow point is epsilon. Now, what we can do then is take a sample from the population, and let's just say that that yellow point that we saw in the previous plot happens to be in our sample as well. And so that's why you see the yellow point there. And, of course, we would have other points in our sample, and using all of our sample values, we can come up with our sample regression model and graph it. And that's what's represented by the blue plane now. So just like before in this plot, the blue line was trying to estimate the red line. Now the blue plane is trying to estimate the red plane, where the red plane is just outlined here so that we can see things better. The distance between the yellow point and the blue plane is our residual, RE. Okay, so that's what we're trying to do now in 3 dimensions. Of course, when you have 3 predictor variables, could you do a plot like this? No, you couldn't. So that's why we just often use the 2 predictor variable case to help represent this. Okay, some notes then. This will help you see where we're going with the rest of the course too. Note number 2 here. So our model, represented like this, is often referred to as a first-order model, since the model is linear in the predictor variables itself. Alternatively, you can look at other models, like polynomial regression models, which we have discussed briefly in Chapter 3, that actually include, let's say, an x-squared term in it. There's going to be a variety of different second order. You could have third order models. You could have fourth order models that are going to contain, like a x squared in it, but also will contain other stuff too. This will be the subject of Chapter 8. Let's see. Number 4 here. So the coefficient on, let's say, just to be general, the kth predictor variable is beta sub k. This measures the effect that x sub k has on what? As you would expect. And just from what we saw in Chapter 1, when we only had, 1 predictor variable. So how would you interpret then the effect that x sub k has on the response? Just like what we did in Chapter 1 with respect to how you interpret a slope. So for every 1 unit increase in x sub k, we expect then the expected value of y to go up by beta k units. However, you have to add one additional point or part to this. And that is we have these other predictor variables in the model. So we have to say, well, let's hold the other predictor variables constant and then look at what's the effect of x sub k on the expected value of y. We'll talk about this some more later on in an actual numerical example. So, number 5. Well, what happens if you have a qualitative variable? Meaning, let's say, political party affiliation. Democrat, Republican, how about we just lump everything else into independent? Sorry if there's libertarians in here, or Green Party, or whatever other parties there are, but let's just say that there are 3 parties. Well, how would you include that in a regression model? It's not quantitative at all. Well, we will talk about how to do that later on. In the simplest case, that will be in Chapter 8. In the simplest case, suppose you have a qualitative variable that has just 2 levels to it, such as gender, male or female. Well, in that particular case, it's relatively easy. How about you set, let's say, x1 to be 1 for female, x1 to be 0 for male, or vice versa. Transform variables. So we can also have, let's say, a log transformation of y or any other kind of transformation as well. We'll talk more about that in Chapter 7. Interactions. If you've had a Stat 802 course, you've dealt a lot with interactions before. If you haven't, don't worry about it. We'll start from the beginning of how to work with interactions. But what an interaction represents is, let's say we have variables x1 and x2 in our model, but also you have their product as well. This is what's referred to as an interaction.
Doesn't that go to the second order model?
It's not quite a second order model, no, but that will be one term in a second order model. Okay? We will talk about that more in...
what I meant is basically this is already part of the second order. Should it be in the first order?
Well, I just was talking about here. This is a first order model. and then I'm just talking about other extensions. I have here more what we discussed this in Chapter 7. I think it's actually Chapter 8, so I think that's a misprint. Sorry about that. So also I refer to this as multiple linear regression as a formal name. Well, where does a linear come from? Well, we talked about this way back in Chapter 1. It comes from the fact that we don't see models like this. Expected value of y, the beta 0 plus beta 1 times x1 plus maybe x2 beta to the x2 to the beta 2 power. That would be referred to as a nonlinear model. So the linear refers to as a linear combination of the betas with the x's. A model like this would be discussed in our nonlinear models class, Stat 974, I believe. Okay, so page 6.9. Some of this stuff we're going to go faster because it's just a direct extension of stuff that we saw in Chapter 5 and actually even previous chapters as well. And then also you'll see why we put everything into matrix terms in Chapter 5. So here's our general model once again. This is our population model. Notice we have I equal 1 to n. So what this basically says, if you did have a sample size n, this is how all the y's and x's will be represented in a population context in terms of the true betas and the corresponding epsilon. Now since I have I equal 1 to n, if I didn't want to actually write I equal 1 to n and actually wanted to write everything out, what I could do is just simply write everything out. Obviously that's kind of long, but you could do that. As long as you have a simple n, but you could do that. But the reason why I do this is, and similar to what we saw in Chapter 5, is this leads you to see how you can represent your model in terms of matrices. So for example, I could call this then my y vector. I could call these epsilons here my epsilon vector. And now look what happens to our x matrix. So in Chapter 5, our x matrix was n rows, 2 columns. Now it's n rows and p columns. So this is an n by p matrix. The first column is still a column of ones, and then every other column corresponds to a particular predictor variable. Our beta vector, before in Chapter 5 was 2 by 1, now it's going to be p by 1. And so notice what happens if I were to multiply this first row of the x matrix by my beta vector. You can see how what we're getting is simply this part right here. Okay. So then we can then represent our model very simply as y is equal to x times beta plus epsilon. That's it. That's our matrix representation. This epsilon, just like in Chapter 5, of course, each epsilon itself is distributed independent, normal, 0 sigma squared. Represented in terms of matrices then, epsilon has a mean of 0 and a covariance matrix of sigma squared times I. So again, each of the diagonal elements here correspond to the variance of an epsilon. So here is variance of epsilon 1. The off-diagonal elements are all 0 because we have independence between, let's say, epsilon 1 and epsilon 2, epsilon 1 and epsilon 3, and so on. If I were to use expectations here, the expected value of y is equal to simply expected value of x beta plus epsilon. Remember, I can distribute that expectation through. The expected value of epsilon is 0. Expected value of x beta is x beta. Okay. What's the covariance of y? Does anyone remember from Chapter 5? Come on, you didn't go home and memorize it after our last class? Sigma squared times put a little -1 here. What's that?
X prime X.
Yep. X prime X. So sigma squared times X prime X inverse. That's what we had in Chapter 5. In Chapter 6, exactly the same thing, but now the X matrix could be bigger. Otherwise, it's exactly the same thing. Again, this is why we go to matrix algebra, because all our formulas just simply continue. Otherwise, if we didn't do matrix algebra, it'd be a real pain to write all this stuff out. A real pain. Okay, section 6.3 then. How do we estimate our betas? Well, remember in Chapter 1 we talked about least squares estimation. In order to find the estimates of beta 0 and beta 1, we simply minimize the sum of squared errors. The values of beta 0 and beta 1 that minimize the squared errors would be our estimates relative to our data. And so we call these B0 and B1. We had nice little simple formulas for them. If we were to do exactly the same thing without matrix algebra, B0 and B1 would be quite messy to actually write out. Very messy. So, in a multiple linear regression setting, we are again going to want to minimize SSE, and it just simply is X prime X inverse X prime Y, just like what we had in Chapter 5. The only difference, again, the X matrix changes. So, X prime X inverse X prime Y. So if I happen to see you walking around campus, I ask you, what's B? You should tell me immediately, X prime X inverse X prime Y. Okay? Did you remember that? Properties of least squares estimators, same as what we had in Chapter 1, all carry through here. So that's good. Section 6.4 then, how do I find Y hat? Just plug in the B's in your model, you get Y hat. Or if you were to do it all with matrices, Y hat's equal to X times B. What's my vector of residuals? E? Well, vector of the Y's minus your Y hats. And your hat matrix, of course, please remember why we call it the hat matrix, because it's a matrix that allows us to put the hat on top of Y. Exactly the same thing, just a different definition of X. Covariance matrix of the residuals, same as in Chapter 5, just a different definition of the X's. Okay, so let's get into an example. Any questions? Okay. So this is meant to be a simple example. Just like how we saw that sales and advertising example back in Chapter 1, simple kind of made-up example, so that we could look at some stuff graphically and get used to some of the formulas and stuff. Same kind of idea here. Here's the background for it. Suppose you want to determine the effect that advertisement size in square inches and newspaper circulation has on the number of advertisement responses. So imagine, let's say, a print newspaper, and there's an advertisement in it. And you would think that depending upon the size of the actual advertisement, and also the corresponding circulation of the newspaper, in other words, the number of people who read the newspaper or get the newspaper, let's say, every day, would have an effect on the number of people then that will see the advertisement and then respond to the advertisement. So you can think of maybe we have 6 communities with each one having a particular store in it that this company's advertising about, and the number of people who go in there and say, hey, I saw your advertisement in the newspaper, I want to buy something. That's what we're measuring then as the number of ad responses. So for example, in the first observation we had 100 ad responses. The advertisement size was 1 square inch, and the circulation of that newspaper was 20,000 people. Okay. So let's look at how we can now estimate the following model. I want to estimate the expected value of ad responses is equal to beta 0 plus beta 1 times the size of the advertisement plus beta 2 times the circulation of the newspaper. That's what I want to estimate. Well, let's use some matrix methods. So x prime x inverse, x prime y will give us our estimates of the betas. Of course, B itself should be a 3 by 1 matrix, so it should be B0, B1, and B2. So I simply, first of all, write out x. Notice it is 6 by 3. I have the leading column of 1s. I take the transpose of it. I multiply it by x again. I invert the whole thing, then multiply that by x transpose again, and then y. So, would you like to do this by hand? I had to do it by hand when I was in grad school. No, we don't want to do this by hand, but you are responsible to be able to understand this, the setup of what these equations look like and the basics of, well, how would you multiply it out? Well, simply I would transpose it, take the first row times the first column, but I'm not going to ask you to do the entire calculation ever on a test or on a project unless you were to use R. So let's look at how we would do this. Since I have such a small data set, rather than reading it in from a data file, I'm simply going to create a vector of my ad responses, the sizes, and the circulations. Put them all in a simple dated frame, and there's my data set. So now to form my X matrix, I combine by column. We saw this in Chapter 5. The number 1 with all the sizes. I pull out size from set 1 and also all the circulations. And also I pull out the ad responses to form Y. So here's my X, here's my Y, as you would expect. Next, let's actually now do x prime x inverse, x prime y. So remember to do the transpose in R, use the T function. To do the inverse in R, use the solve function. To do matrix multiplication, use percent star percent, or percent asterisk percent. And let's go ahead and do it. And so those are my B's. So then my model then is simply y hat is equal to 6.40 plus 20.49 times size plus 0.0028 times circulation. That's my sample model. Now what you'll notice is that basically all I did was I copied and pasted my code from Chapter 5 when we did the high school and college GPA data set. I copied and pasted all my code from basically here on. Because once I define X, all the matrix multiplications, all the matrix algebra stuff just simply holds. So I'm not going to go through it all in detail. I just point out some highlights. If I want to find all my y hats, I simply take x times b. Residuals, y minus y hat. So for example here, when, you got to be careful with how R actually labels everything. This corresponds to size. So this is our, you could say our x1. No, it's x2. R just by default labels the columns as x1, x2, x3, and so on. Here is the circulation. Of course, y is the ad responses. But let's talk about y hat here. Well, how would I find that if I were to do it without matrices? You know, I take 6.39 plus 20.49 times 1 plus 0.0028 times 20,000. So that's the first value in the data set. I get 82.88. Hopefully I did that right. Close enough. There's some rounding error. 82.98. What's my residual? 100 minus the 82.9877 is 17.01. That's my residual. Notice that the largest in absolute value residual corresponds to observation number 5. See that pop up shortly again. How would I find my estimated covariance matrix? So this is for the beta hats. Oops. I'm sorry, for the B's. Note that I call this cov.beta.hat. Probably I should call this cov.b. It's just some books, instead of calling the estimates B, they will call them beta hats. Just make a note here so I can change that in the future. So the estimated covariance matrix of the B's, well, again, x prime x inverse, take it times then the estimate of sigma squared, which is MSE. So for example, this right here is what? What is this 34.6 in our symbolic notation? Variance of B1, the estimated variance. Okay. For example, right here is the estimated covariance of B1 and B2. Okay, so let's talk about how we can now estimate our model again, but in a more simpler way using the LM function, just like what we did in chapter 1 starting. And the way that you do this is actually fairly simple. LM, formula equal your response, y, tilde, your first predictor variable, size, and then to separate this from another predictor variable, you use a plus sign. This doesn't mean that you're adding variables together. It just is a way to say and circulation, x2. So if you by chance happen to have experience with SAS and using proc reg, you would, instead of having like a space, you would just, instead of having a plus sign, you would have just simply a space. So I put the results into mod.fit. Let me actually go over to, tend to do this. Put the results in mod.fit. I summarize the fit as well as I've done before. I'm going to save this summary of the fit so I can do some other stuff with it. Put it in sum.fit. And here we go. So I estimate my model. And we get output that looks just like what we had before, except for now I have a second row. Because now I have, third row, because I have a second predictor variable. And you can see here that in this estimate column, we have exactly what we had before for B. And right now, based upon what you've learned in the past, you can start thinking about how to apply that knowledge to this output here. So for the standard error column, you should have a general idea what that means. For the t-value column, you should have a general idea what that means. For the multiple r squared listed here, you should have a general idea what that means too. And we'll spend time in chapter 6 talking about what those represent. There's some small differences, but still stuff generally carries forward. So this is what the sample model looks like. I already have written that before. You could write it out like this as well, as long as you define what y and the x's are. Of course, always remember to put the hat on top of the Y, because now you're talking about an estimated value. Okay, so how can we interpret this model now? Well, we'll do some basic interpretations. You should focus on the B1 and the B2 there. Yeah.
How to get from the simple way the covariance matrix without going into matrix algebra, but just get, I assume it's the regression, the simple regression calculates.
I'm not for sure exactly what you mean by how do we get there. So let's see.
I mean, without remembering the matrix algebra formula, say you just run the regression, you might get there.
Maybe this answers your question.
Yeah.
So there was I think I introduced a VCO function. Obviously, that's easier to work with than with the matrix algebra. Okay, so let's interpret our model. So the regular interpretation that you would have for X1 focuses on B1. You could say something like this: the number of advertisement responses is expected, or you should probably say that's estimated. I think that's a better word to use. Is estimated to increase by 20.49, the B1 value, for every 1 unit increase, which in this case would be a 1 square inch increase in advertisement size. Now I have to add this extra part there, holding circulation constant. Just to make sure you understand why I have to add this extra part, let's do a little exercise here. Let's say I have y hat at, let's see, x1 equal to 2. Now I said subtract y hat at x1 equal to 1. And in both cases, let's say in both cases, x2 is fixed at 50. So what's going to happen here? I can write out the model. I guess I'll do that real fast. Yes, I went 50,000. So I can write out the model in both cases for x1 equal to 2 and, I have that little thing right there, and also x1 equal to 1. And what does this end up being? If I do the subtraction, 20.49, right? So everything cancels out except for the stuff involving x1. Now look what would happen instead if I let x2 vary. Suppose for the x1 equal to 2 case, suppose I have x2 equal to 50,000 again. But now x2 is equal to maybe 40,000 for the x1 equal 1 case. Sorry if that's kind of small, but hopefully you get the idea. Well, what's going to happen is, am I still going to be at 20.49 anymore? No. So that's why that screws up your interpretation then, because it will be dependent upon what are the values that circulation's at as well. So in order to interpret then a particular predictor variable, you have to hold all the other predictor variables that may be in your model constant. Any questions? Let's look at then for circulation. So the number of advertisement responses is expected to increase by 0.0028 for every 1 unit increase in circulation, holding advertisement size constant. Do you think a 0.0028 increase in advertisement responses is going to be meaningful to someone? Probably not. So this is a case where you have to make a little adjustment to your interpretation to make it meaningful. So if you notice in the data set itself, we have stuff that's measured in often like the 10,000s. Maybe we want to look at what happens if circulation is increased by 10,000. And so just simply take 10,000 now times what you had for B2, and you can see that for every 10,000 increase in circulation, the number of advertisement responses is estimated to increase by 28 people holding advertisement size constant. Any questions? Let's look at another example. Well, how about we actually do some predictions? So let's say that for suppose I want to estimate the number of advertisement responses for if I run a 5 square inch advertisement in a newspaper with a circulation of 50,000. Well, how would I do that prediction? You would take y hat is equal to B0 plus B1 times 5 plus B2 times 50,000 and do the math. Alternatively, in R, what you could do is simply create a data frame that has your values of x1 and x2 in it. Then use the predict function, like what we did in chapter 2. Object equal mod.fit, new data is equal to this new data frame that you've just created, and you get 249.1. So, on average, it's estimated that 249 advertisement responses there. What about residuals? And remember this, the semi-studentized residuals? Well, we could find those. Remember what a semi-studentized residual is? E star, y minus y hat over the square root of MSE. So I can pull out my MSE as I first did in chapter 3. Here is the regular formula that we see for the semi-studentized residuals. Here are my E stars. Do I have any outliers? No, doesn't look like it. Well, let's look at this model now graphically. So I need to graph in 3D. There's a few different ways that you can do this in R. I demonstrate them in my program. We're going to look at mainly one way here that I think is the best. And what I can do is use a function that comes with the R Commander package. Do you remember the R Commander package that we first talked about in chapter 1? Remember how it provided a nice little point-and-click interface to using R? Well, we can actually use functions that are inside of R Commander to do whatever we want. In particular, there's a function called scatter 3D. Scatter 3D will give you a three-dimensional scatter plot of your data. And the way it works is pretty simple. Formula equal, just like what you would do with the LM function. Specify your data. What kind of model do you want? Well, I want just a multiple linear regression model, so we use the linear there. Background color, that's just some things to make it look nice. How about white? Do I want grid lines on my plane that's going to be plotted? Yes, I do, so let's put a true there. And let's see what happens. And I want to actually restart here, because when I was walking through my lecture before class, I changed some options and stuff, and that's not exactly how it would look if you were to do it on your own. So let me just quickly come back into it and highlight some of the code that we would need. There we go. So this is how it will look like the first time that you would use the code. And what we have here is a three-dimensional representation of our data with the plane on it. And the nice thing about this is I can actually rotate the plot simply by clicking on any portion of the plot and then dragging the mouse. So if I, let's say, click here and I drag directly to my right, you can see me rotate the plot. Let's go back to where we started here. So you can see that I have circulation. I'm going to use my mouse as a pointer. I have size, and I have number of add responses there. The yellow dots are our data, and the blue plane here is the sample regression model. And you can see as I rotate through here, you can see how the plane tends to go through the middle of those points. Look at this point right here. You can see the distance at this point is to the line, to the plane, represented by this red line. Remember, this corresponded to the residual that was negative 41. That was this is on page 616. There was a residual as negative 41. So notice how it is actually below the plane. That's why it was a negative residual. And you actually see the distance represented there by the line. So that's kind of cool. You can see some other distances located here as well. And so, whenever you have a 3D plot like this, just a static plot, if you weren't able to rotate, it's not very useful. But when you can rotate it, you can, fully explore the surface itself. It's helpful to be able to understand the interpretation. And obviously, in this particular case, we see as size goes up and circulation goes up, we see the number of add responses goes up, which, since I constructed the example this way, that of course, it makes sense for that to happen. The bigger the advertisement, the more responses you would expect. So it was just a nice little representation of what we were doing in 2 dimensions before with simple linear regression, now with multiple regression with 2 predictive variables. Are there any questions? Now this scatter 3D function actually resides in what's called the RGL library. And I just want to briefly mention, because it's the RGL package. The RGL package is a lot more general use package for 3-dimensional plotting. And I'll let you look at some of this more on your own if you're interested. We'll just typically use the default from Scatter 3D from the R Commander package. But you can clear out what's in the current plot, have some nice lighting, do some stuff with a box, and do a similar plot to what we saw before. And it's hidden. There we go. And you can see this is what it looks like now. You can do other various things in it as well. And we'll come back to this later on, where we'll have some more interesting surfaces to look at in 3 dimensions. Okay. Now, what would happen if, though, we had 3 predictor variables? Well, obviously, you're not going to be able to do a plot like this, or 4 predictor variables, or 5 predictor variables. And so in those cases, you're often just simply relying on interpreting B1, B2, B3, B4, as we had done previously, holding all the other variables constant in the model. This is what we would expect to happen. But still, sometimes it's helpful to actually still do a plot. And if we wanted to do a 2-dimensional plot, in this particular case, we could actually do that by holding the other variable constant, or holding one predictor variable constant. So for example, let's say that we hold circulation constant at 45,000. Notice what happens to our model. Let's put in for x2 45,000. And now I have a model that's a function of just one variable itself. Well, we know how to plot that. How would you do that in R? Well, simply the curve function works. And so in these kinds of settings, what often people will do is say, okay, let's fix our predictor variables at particular values, and then plot it as a function of one predictor variable. So for example, let's say that I want to fix my predictor variable, circulation, at 10,000, 45,000, and 80,000. And now let's plot then the model as a function of size only. in here on my y-axis is our estimated number of responses. And so in this particular setting here, you can see that as size increases, well, number of add responses goes up. But you also see then the effect of circulation too. That as circulation is increasing here, so red is for 10,000, blue is for 45, and green is for 80,000, you can see the effect that circulation has as well. So that's another option for one of these kinds of plots. How did I do the plot? Just real briefly. I just simply used the curve function. We've used the curve function before to putting model on a plot. And I'm basically doing that as well. The only difference is that I'm not using the plot function first to get a scatter plot. So my first call to my curve function does not have, if I page over, does not have an add equal true argument as we had seen in the past when we already had a plot there. So for my EXPR or expression, I have B0 plus B1 times X plus, so B0 plus B1 times X, so X is representing size, plus B2 times X2, or I should say the 10,000 for circulation size. Notice how it can easily get confusing here, because notice how I am pulling out the first element of mod.fit $ coefficients, but that is beta 0. So often what I will do in these situations, I didn't do it here. If I could define, let's say, B to be mod.fit $ coefficients. How do I want to do this? Actually, no, I don't want to do that here. I'm sorry. Never mind. You just need to be careful with understanding that this 1 is representing B0. The 2 is representing B1s. So if I just highlight this code, you can see, well, there's my first plot that came up. And then I simply, for the other values of circulation, I simply use 2 new curve functions and include the add equal true argument. And there you see your plot, and I use the legend function as we did back in chapter 2 to add a nice informative legend to the plot. Are there questions? Okay, so it's a brief introduction to multiple linear regression. We still have one more example to talk about, but I want to briefly pause and take a look at project number 3. So if you have that with you, please take it out.
Just one question.
Yeah.
So when you have more than 2, you can create 3D boards. You put them on the same figure, or
you could plot them on the same figure, yes. I think there might be an example in chapter 8 where I actually do that. I don't remember how to do that off the top of my head. Okay, so similar project to what we've had in the past. You can work in groups of up to 3 people. And again, the tentative due date, or a tentative due date, I should say, is Wednesday, October 24th. We basically, in order to fully do this project, we need to finish some stuff in Chapter 7. So that's why I've set it off to Wednesday, October 24th. If we don't get through the necessary material, then I'll just move the due date back. Okay, so we're just briefly going to talk about part of it, because we've just started introducing you to multiple linear regression. You can't do all the project yet. And this is a continuation of working with the cheese data. And if you remember with the cheese data, introducing project number 1, we actually had 3 different predictor variables. Acetic acid, which you've been working with, hydrogen sulfide, and lactic acid. Now let's put all three of these predictor variables into one model to predict taste. Now you might think then that, well, since I have these additional predictor variables, I'm probably going to get a better estimate of taste. In fact, that's what we're going to do, or that's what will happen. But some interesting things happen as well along the way that you'll see through this project and future projects. So here's my model that I want you to estimate. Part A, find the sample regression model using the LM function. We'll just talk about how to do that. Part B, reproduce all the numerical measures given in the printed output of summary of the results from the LM function. So I want every number that's in that you get in that summary output. Just make sure you're following what I mean. Just go back. So here's a summary output from summary. I want you to reproduce all the numerical values that you see there. I guess I don't need to see significance codes, but I want you to show me all this. Show me the residuals, and so on. I want you to reproduce all that using matrix methods. So the calculations that we were talking about at the beginning of the Add Responses program, a lot of this stuff will help you. I don't think I show you exactly everything. Yeah, I don't show you exactly everything there. But you should have the basic background now to figure out, well, how would I do this using matrix algebra and R. Now, since you're doing a lot of calculations, it's going to be very important for you to organize it in a nice manner so I can find every single numerical value that you have actually printed off. So what I would recommend then is to, try to form a data frame that contains this information, or maybe form a data frame that contains this information so you can print off everything nicely. Any questions about that? Part C, we haven't talked about how to do that exactly yet. Part D, how does each of the predictive variables affect taste? So you're interpreting B1, B2, and B3, just like what we got done talking about. And I think that ends all the stuff that I've at least talked about so far. But a lot of this stuff, again, is just simple extensions to what we've talked about in the past, such as do a t-test, do an f-test, and so on. So you should have a general idea of what you're going to be looking for. We just necessarily haven't talked about the exact details and maybe the small differences that occur from what we were talking about in the past. Okay, so that concludes then our short discussion of project number 3. We'll come back to it once we have more material covered. Are there any questions? Okay. So here's our second example. We're going to be using this data set throughout the rest of the semester. It's kind of a classic data set, so that's why I still like to use it, and has some interesting results that pop up with it. And as you can see, it's a little bit of an old data set. It's involving the National Basketball Association, some data that was collected back in 1992 and 1993. This, to refresh all your memories, although perhaps some of you were quite young back then, but I remember it quite well. This was the glory days of the Chicago Bulls and Michael Jordan, who's also often thought of as the best basketball player ever. And so we have some information about Michael Jordan in our data set, and it's going to be interesting to see then how Michael Jordan is represented then by our model, and how he is fit, how his data is fit by our model. Now, since he is I guess to foreshadow what we're seeing here, since he's considered usually the best player ever. Sorry for some LeBron James fans out here. He's not the best ever. Anyway, since he's often considered the best ever, now you might be want to think, well, how do you think that's going to affect our model then? we have this person who's, let's say, above all the rest. How's that going to be represented by our model? It's maybe going to be an outlier. We'll see. So, the purpose then of this data was to measure the effectiveness of NBA guards. So a particular position that's played in basketball. Typically there's two guards on the court at the same time. And how do you measure their effectiveness? Well, there's a variety of different ways. One way that we're going to just focus on is the points they score per minute. So for example, Michael Jordan played 3,067 minutes that season and scored 2,543 points. So his points per minute, or PPM for short, is 0.8291. Now, if you're a basketball fan, you might be thinking, well, why are we using points per minute instead of the usual points per game? Well, the reason being is because not every guard is going to play same number of minutes per game. So to get a better measure of effectiveness of when they are actually on the court, we should measure by minute versus by game. And so that's why we do this. So, what could affect then an NBA guard's points per minute, PPM? Well, number of minutes that they play per game. Well, why? Well, those guards who are, let's say, playing a lot of minutes probably have their offenses, perhaps, let's say, designed around them to give them more opportunities to score. So because of that, we do need to still take into account minutes per game and use that as a predictor variable. Height. Obviously, a taller guard is going to be able to see over the tops of smaller guards, so you might think height has something to do with it as well. The age. New players who are directly out of college or even high school that go into the NBA, are new to that version of the game, and therefore they might be less effective than other players who have been around for a while. Let's say the tricks of the trade, and those other players who have been around for a while, might be better players. But, if the player's been around for a very long time, they're going to get older, and their skills might diminish as well. So you might want to take into account age. So what I just described to you, then, what do you think might be a possible way to take into account age in a model? So let me kind of draw it out for you. Are you talking about like a x squared? Yeah, and that's what I was getting at. So let's say that we have age here. We have PPM here. And so what I just described to you is something like this. At the beginning of one's career, their points per game might be, points per minute, might be way down here. And then as they mature and get better and better and better, it's going to go up. But eventually they get to a point where their skills might diminish. So they're getting older. And you might see something go down there. Perhaps that's what we could have. This is a hypothesis. And we are actually going to test that hypothesis in Chapter 8. Well, some things that affect then the amount of points that a person is going to score is obviously how good they are at shooting the ball at the basket. There's two ways that we can measure that: free throw percentage and field goal percentage. So FTP for free throw percentage measures how successful players is in scoring points at the free throw line. Field goal percentage measures how successful players are scoring points when they shoot the basketball anywhere else other than during a free throw, without going into all the details behind the game. So for example, if a player, let's say, has a field goal percentage of 50%, that means that on average they make about half their shots. If the free throw percentage is 80%, that means 80% of the time they make their free throws that they shoot. They make 80% of them. Many, many, many other factors could be examined, but this is the information that we had available when I first found this data set. here's what the actual data looks like. It comes in an ASCII text file where the first row corresponds to the variable names. I know that's small, but you can take a look at this on your own. And the other, the data itself below the first row is separated by spaces. So it's a space-delimited data set. Here's what it looks like in a table form. So for example, let's look at Danny Ainge. Does anyone remember Danny Ainge, who he played for? He was a former Boston Celtic and then went on and played with some other teams. And now he is the general manager for the Boston Celtics. And he's made some bad trades over his time there. Without going into details, I don't know why he traded away their starting center a few years ago. Anyway, so Danny Ainge, his points per minute was 0.44. His minutes per game was 26.7. Height was 196 centimeters. Free throw percentage was 84.8%. Field goal percentage 46.2%. And at this time, his career was towards the end of his career, and his age was 34. So if I were to read in the data then, I can simply use my read.table function, as we've done many times before. Notice how I say header equal true, because the first, again, row contains the variable names. And SEP stands for separator. It's a space delimited file. I put the results into my dataset MBA. So let's make this simple for now and work with just three variables, three predictor variables: minutes per game, height, and free throw percentage. So again, I use the LM function, formula equal ppm, my response, minutes per game, height, free throw percentage, data is an MBA, print off the results. This is on page 629. So what is my model? I guess this is actually on 630. Let me do a split screen here. So here's my sample regression model. I have y hat, my response. And of course, it would be good to actually say, y is equal to ppm. And I just simply, as we've done many times before, write out the model. I'm not going to go through the details. Write out the model like this, where I define x1, x2, and x3. You could as well write the model out like this, where now you actually replace the symbols with words. I guess I prefer, if I were to choose, I prefer this because it's more descriptive. Notice again how I put a hat on top of ppm, because now this is the estimated value. So let's do some interpretation then. So for B1, ppm is estimated. I don't know why I'm saying expected there. I think it's better to say estimated. Is estimated to increase by 0.004 for each additional minute per game. Now again, this is a particular situation where it can be helpful to change this to a different numerical scale, such as maybe for every 10-minute increase, so take 10 times the 0.004, this gives you then the change in points per minute. But also, and this is a little bit more complicated. Again, if you're a basketball fan, you're used to working with points per game versus points per minute. We could transform this to points per game as well, but the problem is you're going to have to make an assumption of, then, I guess easy for this particular variable, make an assumption of the minutes per game. So you could do that as well. Notice how I also have holding the other variables in the model constant. So at least it's estimated now that I have a positive relationship. As minutes per game goes up, Points per minute is estimated to go up. Height. Height goes up, minutes per game goes up. So ppm is estimated to increase by 0.0035 for each additional centimeter in height. Free throw percentage, this makes sense. As the percentage goes up, you expect points per minute to go up as well. And in fact, it does. Okay. Let's finish this off. So let's look at the estimate of points per game of a guard who plays 39 minutes per game, 6'6", and has a free throw percentage of 83.7. That ends up being Michael Jordan's number. So I simply put in the corresponding predictive variables into my model, predictive variable values into the model, and I get 0.51564 points per minute. Note that Jordan actually had a points per minute of 0.8291, so we see some distance there. And in fact, translating this to points per game, take points per minute times the number of minutes it plays per game, I get an estimate of 20.3. His actual was 32.6. So let's think about what this means in terms of this sports context. This is saying that he is way exceeding the expectations of someone with his minutes per game, his height, and his free throw percentage.
Can you say that without normalizing it to semi-student residuals? You don't know what the...
Well, we'll look at semi-studentized residuals coming up. Okay, we will look at that aspect. But, you know, I like to think of this in this context because this is a numerical scale that, if you're a basketball fan, you're more used to seeing. And then if we take a look at someone else, let's look at John Stockton. For those of you who are basketball fans, what's John Stockton noted for?
Short yards.
When he first joined the game, yes. But in terms of his playing ability, what was he noted for? His assists. Okay, I mean he's a Hall of Famer, just like Michael Jordan, but he's noted more for his assists rather than his scoring ability. So with John Stockton, let's put in his particular values into the model. We get an estimated ppm of 0.4489, but look at his actual, 0.4325. Translate this into points per game. Look at that, 15.7 is the estimated. True value is 15.1. Notice how his value is so much closer to what we would expect on average to happen based upon this model. Well, let's again translate this into a sports context. Does anyone think that, for those who are basketball fans, think that John Stockton was exceedingly good at scoring? No. He was good at assists. Sure, he scored points well, but he didn't really necessarily excel at that aspect. And so we see now with our model that he's doing pretty much like what we would expect, someone with those same predictive variable values. Now, if we were to look at assists per minute, I bet we would see something similar to what we had with Michael Jordan. Okay. Are there any questions? That's it for today then.